I'm Richard Pickings at BridgeSite Software. In this tutorial, I'll discuss some of the advanced bridge geometry capabilities in PGSuper. Our last tutorial discussed features for laying out spread girders on an I-beam slab on girder bridge. This time, I'll go over some advanced features for bridges with adjacently spaced girders. I'll also cover some topics on live load distribution factors and how to interpret PGSuper's status center. This is the start screen for BridgeLink. I'll be running our PGSuper Professional product, but all versions of BridgeLink work basically the same for this example. PGSuper has already been configured for the TxDOT. First, I'll go to File, New, go to the PGSuper Project Templates, Box Beams, and select the B34 with slab template. You can enter project properties if you want. So here is the template. The first thing you might notice is that the template uses mixed width girders. We have 5-foot wide girders at the exterior and 4-foot wide girders at the interior. By mixing 4 and 5-foot wide girders, a wide array of deck widths are possible. We explored mixing girder types a bit in the last tutorial, but let's see how the TxDOT template specifies this. I'll go to Edit, Bridge, and go to the layout, and I'll edit span 1. Then we go to the Girders tab, and you can see on the Girders tab that the girder types are defined span by span. So this grid contains the girder types that are available in this bridge. And Texas, the person who developed the template at Texas has decided to leave this grid expanded. I'll go ahead and join these grid cells together by selecting the grid cells using Shift left mouse. I can right click now and say join. This more compact view is a little bit easier to see. I'll go ahead and click OK here. And I'm going to make this a one-span bridge by clicking here at the span row and removing span 2 and 3. I'll go ahead and click OK. Now here's our bridge. The available options for girder spacing are different for each beam type. For example, adjacent spacing probably never makes sense for I-beams, so that option is not supported. I've chosen a box beam bridge here because I think of box beams as the Swiss Army knife of spacing options. Box beams support almost all of PGSuper's available spacing options, except for the adjustable flange width options found on some decked girders. Looking at the section view, you might notice the red dots at the bottom center line of the girders. They indicate that the working points used to lay out girder spacing are at the bottoms of the girders. For spread spacing, most agencies place work points at the top, but for adjacently spaced beams, it varies by preference whether the work points are at the top or the bottom. That's what's nice about PGSuper. You can enter beam spacing as it's specified on the plan sheets. I'll add super elevations and explore some girder spacing options. To quickly edit super elevations, I'll double click on the top of roadway line right here. This brings us to the roadway cross sections tab on the alignment description, and I'll enter a fairly radical ground super elevation, just to help explanation here. The thing I also want to look at is the girder widths. These are 4-foot and 5-foot wide beams from TxDOT, but often the beams aren't exactly that width. So let's take a look. The 4-foot beam is the 4B34. If I view the section, I can see here that the width of the beam is 47 3/4 inches. And likewise, the 5-foot beam is 59 3/4 inches wide. I can bring up the bridge description dialog by double-clicking anywhere in the white space on the bridge view. The General tab of the bridge description has the major girder spacing options. It's pretty much the whole bottom half of this dialog. As we can see, our working points are at the bottom center line of the girders. Our spacing type is adjacent with the same joint spacing in all spans. Our joint spacing is 1.5 inches and is limited between 0 and 2 inches. This spacing range is specified in the girder library entry. Spacing is measured normal to the alignment at abutment pier lines. And the girder orientation is normal to the roadway. We also have an option to make the orientation of the girder plumb. So I'll go back to the view and discuss those values. As we mentioned, the work points are at the bottom of the girder. The spacing is 4.104 feet, which is equal to 47 3/4 inches plus our 1.5 inch joint spacing. As you can see, the input joint spacing causes the values at the bottom work point to be exactly what's specified. Here at the top, our spacing is wider because of the change in angle at the crown point. Let's go ahead and move the work point to the top of the girder. So here we go, working point at top center line of girders. Now, girder spacing takes place at the top of the girders. And as you can see here, our two centerline girders are probably colliding. This is one of the reasons why it's better to have the work points at the bottom of adjacent girders or girders that are not plumb. I'd like to make a quick note about joint spacing and adjacently spaced beams in general. In PGSuper, girder spacing is always measured horizontally from centerline to centerline girders. When joint spacing is input, PGSuper computes the girder spacing based on the maximum width of the girder plus the joint spacing and using a small angle assumption. This means that the spacing doesn't change even if a very steep super elevation is entered. So don't necessarily think of joint spacing as the joint width at some elevation between girders. I'll use the undo feature to go back to our original configuration. One final note about work points. I'll change the girder orientation to plumb. And as you can see now, the girder spacing is the same at the top and bottom of the girder as you might expect. So it doesn't matter if the work point is at the top or the bottom of the girder for plumb girders. I'll go ahead and change the work point to the top to demonstrate. As you can see, spacing is the same as it was before. Again, I'll hit undo twice to go back to our original configuration. Next, let's explore some of the more of the spacing options for box beams. And I'd like to note that slab beams behave in much the same manner. Over the years, we've had several engineers ask us to allow overhangs on adjacent box beam bridges. So let's see what it takes to do this. And I'd also like to note the spacings here of the exterior girders is about 4.6 feet, and the interior girders are about 4.1 feet. So I'll double click here on the deck to bring up the deck geometry and materials tab on the bridge description dialog. And from here you can see that you can't change the edge of deck. The width of the roadway for this type of bridge is simply equal to the width of the beams plus the width of the joint spacings. So let's see if we can get around this. I think the only option here would be to change our girders from adjacent to spread spacing. So I can check here, same spacing for all girders. Okay, it looks like a lot happened here, so I'm going to change this back to adjacent. And let's focus on the three items down here at the bottom of the dialog. There's the connectivity, the deck type, and this note down here about live load distribution. So I'll change to spread spacing, same spacing for all girders. And what I see down here is that connectivity is no longer an option. This is because we have spread girders and they're not connected. The deck type has changed from a composite overlay to a composite cast in place deck. We can't have an overlay because we have spread girders. And also the live load distribution factor type has changed from a type F or G to a type B. Let's bring up an image from the AASHTO LRFD Bridge Design Manual to look at the bridge types. Now, as you can see in this figure, the type F and G are adjacent girders, and they're connected together to avoid motion between the two adjacent girders. But now we have a type B, and that looks like a widely spread girder. I wonder what's going to happen here. Let's go ahead and change the deck width and the deck thickness. I'll just make it 8 inches all the way across, and I'll put a 14-foot offset on either side. So let's look now at our bridge. Okay, it's telling us that our slab offset must be larger than the gross slab depth. So I'll go ahead and enter an A dimension here of, let's say, 11 inches. That'll give us a 3-inch haunch at the bearings. As I click OK, looks like we didn't add enough deck width, so I'll go back and change our deck width to, let's say, 17 feet. That'll be 34 feet. And hit enter. Okay, now we have a bridge with overhang deck and not quite adjacent girders. If we look here, the allowable spacing is 4.979 feet or more, and then we're right at that. So we can't change this girder spacing to what we want from here. But let's go to the layout here, and I'll edit the span and go to the girders tab. Here's our girder definitions as before, and I want to change this to girder spacing defined span by span. I can right click at the top of this grid and expand the grid, and I'll go ahead and shift click here and join these together. Enter 4.6 feet, 4.1 feet, and 4.6 feet. And I need to do this also down here at the end of the span. So I'll expand join these together. 4.6, 4.1, 4.6, and I'll click OK. This is allowed. One thing, let's look real quick here. You can see that the allowable spacings are now closer. So we're able to input the widths that we want. I'll go ahead and click OK. And here's a bridge that looks a lot like what we want. Maybe the overhang is a little silly, but at least we have what it looks like. Let's go ahead and try to run a spec check on girder B. Okay, we have a problem here. Live load distribution factors could not be calculated for the following reason. The beam spacing is out of range. It's too small. See table 4.6.2.2.B-1. And it's saying a refined method of analysis is required for this bridge. I'll dismiss the dialog by clicking OK. Now the spec check report window says the following error occurred while updating the views. So this is the same note we saw in the little dialog before, and it's telling us to see the status center for details. If we go to the bottom here, we'll see a red number 1. I could double click there to bring up the status center. And same with this red icon up here. I'll go up to View, Show Status Center. Okay, most of the items in the status center dialog here can be selected, and if you double click on them, it will bring up a solution for the problem you're looking at. And let's take a look at these options that it's giving us. We could directly input live load distribution factors. We could use the LRFD equations regardless of the range of applicability limits. Use the lever rule where only we're outside of the LRFD range of applicability, or we could use the lever rule for all live load distribution factor calculations. Whenever you run into this type of an error in PGSuper, you need to put your engineering hat on and get to work. So let's take a look at the ASHTO table that it's referring to. Okay, now we have a type B, if you'll remember. We have spread spacing, and we used to have a type F girder. These equations look a lot different. I am not comfortable at all just swapping the equations out for another set of equations. As you can see for the type B, the girder spacing range begins at 6 feet, and we're looking at only 4-foot spacing. So that, to me, is not an option. I also don't like the fact that these two equations look completely different. So I don't even want to use the lever rule where it's outside of the range of applicability limits. I'm not going to give you guys engineering advice here. This is really something where you need to do a sensitivity study, or you need to contact the agency that you're designing the bridge for and see what their recommendations are. What I will do, however, to keep the tutorial going along, is I'm just going to click on Use the Lever Rule. The lever rule is typically conservative. Not always, but typically. So I'm going to do that just to keep moving. Okay, this brings us to the live load distribution factor dialog. And we can see that the status center is pre-selected compute all factors using the lever rule. Frankly, for this particular example, I would be more comfortable directly inputting the factors, but you're going to need to do a hand calculation outside in order to make this happen. I'll click on OK. Now our error has been cleared and the status center is green. So we can continue our analysis. When this is the case, it's very important to look at the calculations that the program's doing. So I'm going to bring up a details report. I'm going to click here. I'm going to unselect all of the chapters. I just want to look at a couple of chapters here that are very important. One here is loading details. Live load details is also important. And then there's a detailed description in live load distribution factors here. So I'll click OK. Go use the table of contents by right-clicking, and I'll first look at the loading details. This is hugely important in any analysis that you run, to look at the dead loads that were applied along your structure and make sure that they make sense. Scrolling down a bit, here's our live load distribution factors, and they're all computed using the lever rule as we requested. Some tools that might help you run your sensitivity study are available at the TxDOT website shown above. These are spreadsheets you can use to compute live load distribution factors. There's quite a bit more work to be done here on our bridge to make it a real production bridge. Things like detailing, adding dead loads for loads like shear key loads, and figuring out that live load distribution factors are still needed. But we've run out of time today for this video, and I hope you've learned a lot about how to do girder spacing for adjacent girders. This is Richard Pickings wishing you happy bridge designing.